In this video, I want to show this notch filter that I built some years ago. It's got two BNC connectors on the back, and I needed this filter to eliminate the FM broadcasting spectrum from my receiver scanner, which was a wideband receiver and was not protected enough against those strong signals that would saturate my my receiver. And my main interest was to listen to the aeronautical band that's between 118 and 136 megahertz, so close by the FM broadcasting, which is between 88 and 108 megahertz. So I remember I found a little project on internet, and I've used this little box for candies, and it's basically is an LC filter. It's not it's pretty rudimental, but we will take a look at how it works. So it's not unidirectional. You can connect it either side. This can be the input and then this the output, or vice versa. So the inputs, obviously, all the metal box acts like ground. So basically, looks like a pi, because we've got pi network, because we've got two inductors towards ground, and we've got these three trim caps and this inductor in the middle. I don't have now the project on hand, but yeah, I'll try to look for it. I think I put this ceramic cap to get the value that was needed. I honestly don't remember. I just copied the project without knowing too much about it. There's also this third trim cap here across. So first of all, let me try to find this little project. Maybe I can still find it on internet. Then we will take a look at the frequency response using the Marconi and the spectrum analyzer with the tracking generator function. I think we are already set. We've got a center frequency of 98 megahertz, and we've got 10 megs per division, so we should have a notch around the center, because this will be 88, 78, okay, and 108, 118, okay, we can change the span there. So yeah, let's see. Okay, I found this page. I don't know if it's the one that I used back in the days, but anyway. So we have this Chebyshev bandstop filter designer. We've got two configurations. One is pi, one is T, and mine is the pi one. So we've got the first element is the shunt of the series LC, and then we've got the parallel of LC, which is the one in the middle, and then we've got the third element. So I put the numbers, the figures for what we want. The Center frequency 98 megahertz, as the FM broadcasting band goes from 88 to 108. The bandwidth that I put is 20 megahertz. I left the passband ripple to what it was. 50 ohm impedance, third order with the first element being shunt. So the calculator came up with this informations for the capacitors and the inductors. So we've got the two shunting elements are 6.8 puff with 385 nanohenries, and the parallel element is 138.7 with an inductance of 19 nanohenry. I could try and measure those, but for now I'm going to connect the filter to the test set and see how it performs on the spectrum analyzer. Okay, so we've got the filter connected in line. Signal comes out from the TNC port and goes into the N port. We are already set. Let me set the ref level to, I don't know, -10. It should be the level, output level that I selected for the generator. If I switch the truck engine on, we should see something. Oh yeah, obviously the right frequency is not correct, so let's go on the ref frequency 98 megahertz, and now we've got the response. There you go. So that is the response. Let's put a marker on. So we're looking at 88 megahertz. We are already let's do it differently. Let's go for a level of 0 dBm. So we go to 0 dBm on the ref level. Okay, so 88 megahertz. It's not 88 yet. Marker 1, 88, yeah, 88 megahertz. We're looking at minus 10 dBm. So basically 10 dB of attenuation, which is a bit low considering that we already have some station here. So we can say that the notch filter is not maybe wide enough. We reach a maximum attenuation here of 40 dB, which is good, and is reached towards the center frequency. Then we've got the a crest or peak where the attenuation diminishes by 10 dB or so. Then we've got another dip, and then we go high again, and we reach the other side, 108 megahertz, and we are minus 12. So if we put the two markers on the edges, let's say here we've got minus 10, and marker 2 at 108 we've got minus 12. So yeah, that's the result for now. We can try and tweak the caps and see how it performs, how it changes the response. Let me try to position the camera. Okay, so this is the frequency response. Let me try and get the everything. It's not easy to see with the camera. If I switch the light on, let's see if it's any better. Maybe a little bit. Okay, let's now open this box and try and tweak this notch filter. Let me see if I can get in the shop. First of all, if I open the box, the response changes slightly, but it's fine. So I will try first the let me see, the input now is let me check what is the input. So the input is this one on the left and the output is this one. So I'll try the first element and let's see the response. Obviously we can also try and change the inductance. Alright, this is, I think, at the end. This is kind of stuck. Yeah, there you go. Okay, we've got a big change, as you can see. The notch has been shifted up, and the attenuation has gotten worse. These trim caps are not easily tunable. I will try to do my best. Okay, now I'm going down in frequency. As you can see, I'm kind of incrementing the attenuation on the lower edge, which is marker 1 at 88. Now we've got 20 dB, so we have increased the attenuation by 10 dB. And now if I go on the output cap, let's see what we can do. Let's see what is the response, if we can change anything. Okay, this is not changing much actually. Maybe the cap is not working well, the trim cap, so I'm not getting much of a change. Okay, what if I move the first shunt inductance? If I get less inductance, if I increase the spacing, see, I have increased the spacing. Now let me increase also the output. Okay. Right. So we've got now, as I said before, better attenuation on the first edge. Also overall better notch attenuation, but we got worse now attenuation on the upper edge, slightly worse. If we go and tweak the parallel LC in the middle, let's see what happens. Okay, now we are like kind of widening the filter. Okay, which is, by the way, also producing, see, we've got a wider response, but we have now a much higher response here in the middle. So I will try to take this off camera as best as I can for the FM broadcasting band, and then I will come back with the result. Well, now I have tweaked the filter as best as I could. It took a while, but eventually this is the probably the most satisfying to me result. Is symmetrically enough, not the best shape, but ideally I don't want this this peak here in the middle. I want it to be kind of flat, but couldn't manage to have a better result than this. If I open the box, it gets better, a bit better actually. Anyway, basically, if we take a look, at the marker 1, which is this one here, which is now set at about 80, almost 80 megahertz. We've got only 4 dB loss. I'm saying this because there's another frequency band used by public services below that edge, so ideally we want that to pass through. And if we go up in frequency towards the 87, 88 megahertz, we have already, and now 87.6, we have already more than 20 dB attenuation. And regarding the marker number 2, I've got the 108 megahertz, and I've got 20 dB 0.7 as well. So everything in between those two edges is below 20 dB, which is not too bad. But actually, we've got even more now. We've got here we have more than 40 dB. So the only part which is less than 30 dB attenuation is this small peak between 97.6 and 91.2. Obviously, if we find out with a spectrum analyzer, with an off-air test, if we find out that there's a station which is stronger than the other ones, maybe we can tweak the filter and tailor the filter for our current situation. But yeah, that's it. That's the result. So overall, we can say that the attenuation is generally more than 20 dB on the entire band, and even more than 30, up to 40 on the maximum value. So that's all for this video. Not the best notch filter. Would be interesting also try to create maybe some filter with coax cable with stop. But yeah, I'm not using this filter anymore, because then I bought a commercial FM notch filter made by, I think it's called SDR Play, something like that. I bought it on internet, on eBay, I think for 25 euros. It would be interesting to check that one as well, but I don't have it here at the moment. So that's all for this video. I hope that was interesting to somebody. All the best. 7-3 to the next one. Just before I finish the video, let's have a look at how the filter works against the FM broadcast band. So now we are visualizing on the spectrum analyzer the FM broadcast band. I put a couple of markers. So marker number 1 is at 88 megahertz. Marker number 2 is 96.7, which are 2 strong stations. Actually, we've got also, this one is also strong. This one here, 104.5. Well, let's monitor these 2 particular stations and the overall spectrum. I have connected this wire. I will now disconnect this interconnection and put the filter in between, and we see the results. Let's do it on camera. So connect here this, and I connect this on the other side. That's the result. So as you can see, the first station now went down to almost minus 70 dBm, and the second station has gone down to minus 81, and those were up high. So the overall FM broadcast band has gone very low, with maximum peak at around minus 80 dBm. Let's go back. Actually, let's do this. Let me see. Should be able to keep the maximum. Single repeat. Yeah, if I should, let me see. Yeah, max hold. Yeah, that's it. Or maybe just single. Yeah, let's just do a single sweep. Single sweep, and then we disconnect and we connect directly this Y antenna, and we sweep again. So now we will see the difference. 3, 2, 1, go. That's the difference. Oh, that's good. That's good difference. So yeah, it works. That's all for now. Bye bye.